You're welcome. You're welcome. So like, if you want to work on this on Friday, transition. See, I like the stuff's not required.
Okay, so let's get started. As you remember from last time, I stopped in the middle of the perception lecture. So before we continue there, I just wanted to check in. How's everybody doing the homework? Any like major questions that we should discuss in a classroom setting?
I'm having issue with this scale, like arranging or like the graph to be having like margins with the axis.
The bar chart.
Yeah.
Well, yeah, that's something that maybe is not the best for classroom. Like, I'm happy to look into it in my office hours later. Or
is it like a math problem? Like, I should like understand.
so you mean by where to put it?
Yeah. So like push the graph towards, like transform the graph to the right position.
It's not obvious that it would be a problem. It shouldn't be like there's not terribly like there's just addition, subtraction, though, or more advanced math. Any other comments?
This is kind of a minor one, but when I use the HSL color and it converts it to an RGB color string,
Yeah.
it doesn't seem to do a correct conversion because I did the comparison in Photoshop and so one of them is wrong.
Okay. Well, it would be tragic if Photoshop were wrong. But so what you're saying is that if you put in an HSL color and you convert it using this D3's built-in converter.
Well, because you have D3.HSL and you give it the hue, saturation, and luminance or lightness, right? And then it converts it to an RGB string for CSS properties. It doesn't seem to do the right conversion.
Is it like off by a little or off by a lot?
It's off by a lot.
Okay, I would like to see that and look into that, but I don't have an answer for it.
Okay, all right.
But generally, that shouldn't stop you from.
Yeah, I'm just wondering.
Yeah, no, I've never heard of it, and I would be surprised. My guess is that there's some different configurations,
Okay.
but that you're using a different color model in Photoshop than you're using in D3. That would be my best guess, but other than, I would be surprised if the color conversion is wrong in D3 or in Photoshop. Any other comments? Yep.
I haven't used WebStorm yet, but I was wondering if you had a library, is it able to parse it and give you suggestions?
Yes.
Oh, it can.
It will do code completion. It will. I use, for example, WebStorm, add in the libraries, and then use JSLint, and it will warn me about every missing function or every undefined function. And
even for the D3 library?
yeah.
Interesting.
Yeah, it's actually pretty easy to do. Like you basically hover over the library link where you include it, and then say add this to the local installation.
Can you repeat that question?
The question was about how we can integrate the library as part of WebStorm, so that WebStorm is aware of which features are available in D3. It will warn us if we don't correctly use it and can use autocomplete and so on. Yes, all of that is possible with WebStorm. Okay, great. Another note that Carolina should mention that she forgot to put in her office hour for this week, but she just did that. So Carolina's holding office hours after the lecture, right? In the usual room. And I also have office hours after the lecture.
And homework and solution.
Yes, and the homework 2 solution was just posted, so if you want to take a look at that, feel free to do so. Okay, so we talked about perception and about the fundamental biology, about the difference between cognition and perception, and then we started talking about change blindness. And so, like, the point here is that if we change things, we don't necessarily notice that things are changing. So, for example, if you design a visualization system that does some gradual transition, you cannot be certain that a user will notice that. So we had these examples with like intermittent pictures, and in this case here, the shadow is missing. In this case here, the box is missing. And here we are missing the turbine from the airplane. There's a couple of other things that are interesting in that context. So notice whether you know, like, raise your hands when you notice any change here. Three, four. That's less than 10% of the class. I'm playing it again. Three, four more. So what has changed?
Shadow.
Yeah, so somebody has actually like mowed here. If you look closely. So such a gradual change is hard for us to pick up. Here's another one. A couple of people. Okay, so look at this stone here. So all of these tricks, they're based on essentially taking or adding or removing an element that is not exactly in our focus. So as I mentioned last time, if there were like a person standing in the middle of the picture and we would remove this person, then of course we would notice. But here's another example. I like the picture. Did anyone notice something? One person. I'll give you a hint. This time it's not about some peripheral objects. It's actually on one of the people. So look at the fashionable lady's shirt here. Whoa. So there's a subtle color change from blue to red.
I still didn't see it.
You didn't see it?
You pointed it out.
Okay. Maybe your angle over there isn't the best. It's not extreme, but it is.
Could you show the beginning and frames?
Sure. So here's the beginning, and then here we have the end.
Now I see.
So this is not, in this case, it's not about the object, but this object is important for us in the picture, but it's really Like here we don't notice is the color because we don't care about the color. We don't parse the color all the time. We simply look at the scene and extract information from it. This is another one.
Brief silent movie. Now, this is a movie perception test. Watch this brief silent movie and then I'll ask you some questions about it. You saw a person get up from a desk to answer a phone, right? Did you notice anything change during the video?
So did you?
His shirt?
I think so.
His shirt?
And his glass, right?
Yeah.
Was it a completely different person?
The video featured different actors wearing different clothing. Watch it again. Most people don't notice the change, a phenomenon known as change blindness. This video is from research by Daniel Levin and Dan.
So this is for change blindness, but then there's another thing which is called attention blindness. And so here's another funny video.
Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, sir.
I was planting my petunias in the potting shed. Constable, arrest Lady Smythe. But how did you know? Madam, as any horticulturist will tell you, one does not plant petunias until May is out. Take her away. It's just a matter of observation. The real question is, how observant were you?
Anybody notice anything weird? One or two things? Oops. Sorry.
This is a movie perception test.
The leg of the person.
The real question is, how observant were you? Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, sir.
I was planting my petunias in the potting shed. Constable, arrest Lady Smythe.
Yeah, so the point of this is traffic awareness, and like I have one more video. It's just a good now to show.
This is an awareness test. How many passes does the team in white make? The answer is 13. But did you see the moonwalking bear?
So notice how you were actually primed to pay a lot of attention here, and still you missed probably like 80% of the things that changed. And so why I'm showing you this? Why is this relevant for visualization? Well, to find meaning in what we see, we must selectively pay attention to what is important. And so our low-level vision is driven by object features rather than by conscious effort where we look, but the attention is driven by our pre-existing knowledge, by what we pay attention for. So what it means is, if you design an interface, and that's not just something for visualization, that's sort of for any kind of human-computer interaction, like people will not notice if you do something subtly. You cannot be guaranteed that somebody will read this, will see this, and so on, unless you really take care of bringing it to people's attention. So that's why you should really take care of like making things explicit and don't make assumptions about everybody will see what you're doing here. Okay, so this moves me on to Gestalt principles. Gestalt principles are by the Wiener Gestaltschule, Wertheimer and others in the 20s observed, like these were psychologists, the circle of psychologists, and they observed that there are certain patterns that transcend, where we kind of like make interpretations and that transcend other properties. And so what the next couple of things I'll show you is Gestalt principles or recent observations that also fit into this category. Just a historical note, these guys, Wertheimer specifically, may like observe those, but he also had explanation for them, and it turns out that his explanations for why we perceive it like this were not true, but his observations are still valid. So, for example, Gestalt principles are things that connect a contour, things like proximity, things like alignment, common movement, common texture region, common color region, and enclosing contours. So anything that we can use to group or to show relationships. So, for example, here we perceive this here as columns and this here as rows because of proximity. Like we see this as lines and this as lines because these dots here are further apart. And so proximity, like if you think back about the pre-attentive features, proximity is a very strong grouping principle. So if I were to ask you and show you this picture only and ask you highlight the two groups, you wouldn't say the orange ones and the black ones, you would say this group and this group. So proximity is a very important grouping principle. So yeah, here's an example of how that would look like in a scatter plot. So like this is used quite often, and often in so similarity is often expressed through proximity in some kind of multidimensional projection, for example. Yeah, here are other examples for similarity. We have a similarity by color. So here we will group it by color in these various examples. You can also like formulate this more generally. It's more of like a co-modulation of a visual channel. For example, color, shape, size, value, orientation, texture, adding a glyph, adding a label, adding a frame, adding background. So here we're grouping by color, grouping by shape, grouping by value, or grouping by adding a glyph. However, and as I mentioned already in this part of the lecture, in the previous part of the lecture, these things are pre-attentive for a couple of colors, for very few actually, but here, like here, the two red points are easy to identify. Here, the two red points are not easy to identify. So there's perceptual issues with that. And it is also slower in a cluttered environment. So here's this example with highlighting search terms in an interface. And who can, like how many dots, highlights do you spot? Who sees 3? Who sees 4? Who sees 5? Who sees 6? Okay, so there's actually 6. But this one here is rather small and has a little contrast to the background. And then here we have another one which is rather small.
Aren't there 7?
Then I missed one.
Is there one in the picture in the top left?
1, 2, 3, 4, 5, 6.
There's one in both pictures on the left side.
I don't see
I think
one
the
here.
top one isn't a dot.
It's the roof of a building, I think. but that's exactly the point. They're difficult to spot, difficult to identify, and unfortunately, like for example, when I use the Finder or the preview for PDFs in Adobe, not in Adobe, on Mac, and I search for a term, that they use such a subtle color to highlight it, and I basically can never find it. And I find it super annoying because this would be so easy to correct. You could also, instead of highlighting one element, you could modulate everything else. So people have tried to blur everything else and then get you to focus on this. Or if you remember Windows Vista, to get your attention on the nasty pop-ups all the time, do you want to allow this, do you want to allow this? They always faded everything else into the background and only showed you the mode dialog, not darkened. So that would be also an option. People who perceive those things as pretty annoying, typically. So don't you do it unless you have good reasons to do so. So here are two real examples from papers here. People have studied at CHI how people would find this particular button, and they have shown that there's a significant difference in finding this button, of course. And then people also have studied this for brushing based on scatter plots. So my recommendation for doing something like this is don't use this unless your sole objective is to guide attentions toward one particular set of items. If the context plays any role, don't do that. And so here's a little experiment now. Proximity, color, size, shape. All of those are now clearly grouped, and now I'm going to make just one change. And this overrides the grouping completely. Now, in your mind, you're grouping by connectedness. So even if these things are close, even if they're of the same color, even if they're of the same size, same shape, you will always group them mentally by these links, by these connections. So connectedness and common regions are extremely strong grouping principles. You can do that with connecting them via link, via surface, via an outline. There's subtle differences, but it doesn't really matter. So these are very strong grouping principles, and they stand out quite a bit. So here's an example where we have a guy who's connected this in a paper to show like relationships between items of one cluster to another cluster by tracing those lines and bands through here. That's one example of how you can make use of connectedness. Enclosure is kind of similar to grouping, but it's probably even overrides connectedness. So here, in this case, you would still think that this enclosed thing here is highlighted or grouped. Here's another example. There's a couple of different varieties, like different papers, how people have used connectedness to highlight set relationships for points on maps. So here is a technique that's called bubble sets. Here we have like a continuously drawn line, and then here we have branching trees, and people have actually studied which is more effective and so on. Turns out the differences are rather subtle and most of them work. One problem with all of those is of course that they include information on the underlying image. So another Gestalt principle is continuity. What do you see here?
Circle and square.
Exactly, that's what you think you see. But you make assumptions, right? Because you like make assumptions mentally that things are continuous, but it could even it could easily be this kind of shape. It could easily have like the circle could have this kind of shape, or it could have some non-regular shape. You don't know, but you wouldn't have thought about it. You assume continuity. So we kind of like make these assumptions that things are smooth and continuous, and it's easier for us. We wouldn't think that these line intersections here, like this would go apart like that. We would rather assume that this is one part and this is one part. And it's also easier for us to trace links between items if they are continuous. Like, just makes more sense to us. And then we can also deal easily with occlusions and ambiguous crossings. So this is again an example from my own work where we started out with using continuity, but we kind of like had discontinuous breaks in here. And then we refined that by using like simply a continuous rendering, and it turns out that the results are much more convincing and much easier to follow. Another example of a Gestalt principle is closure. And so here we simply mentally fill in the contours. So there is no border here, but we all know and see that the shoe is like, this is the end of the shoe. It doesn't like bleed over into the canvas here. And the same here for the Panda bear or for all of these pictures. We see shapes even if we have only very, very limited indications that they exist. So we see here these two different shapes, even though we only have those little circles, and just by themselves they would be meaningless, but we infer the shape through the principle of closure. We really like symmetric things, so here we don't really know what is the figure and what is this exactly, but this is clearly a figure. And the same thing here, we assume that this is not a continuity problem, right? Here we assume symmetry. We assume that this is really a cross. And so where this plays a role in visualization is, for example, we are really good at spotting errors in symmetry. So if you look, for example, at the population pyramid, and so we have in a population pyramid, this is the number of people in a population that are of a certain age stacked up to each other. And then usually what you see is some kind of asymmetric behavior. Women typically live longer than men. So you see that here women have like a stronger, have higher bars, longer bars. And that is easy for us to spot perceptually because we look for the symmetry and we are kind of disturbed by the lack of a symmetry. And yeah, these charts are kind of interesting to look at, and these can often highlight particular events in here. And then sometimes, like these MC Escher pictures, they are playing with the concept of figure and ground, right? So here you could either see, like who sees a cup? Okay. Who sees faces? And I guess now everybody sees both, right? You can switch between them, but it's like there's no clear distinction between figure and ground in these pictures. So what are the applications in visualization for this? This is also like going back to this picture that I showed you before. There's also a paper that I wrote a while ago. And here we thought about these highlighting techniques. So we played around with a couple of different visual encodings. So here I have blurred everything but the highlight terms. And this is not great to spot. So there's machinery, general, fishing, and then these dots in here are basically impossible to spot. Darkening works somewhat, but it's also not perfect. Red, as I talked earlier, works, but it's not perfect. We could make it blink and make it really annoying, and it will be easier to spot, but blinking generally is never a good visual encoding because it simply draws your attention. Or we could use connectedness. So that's what we tried out in the study, whether people performed, like how quickly and how correctly people perceived all the elements in an image. And so we used this, what we call visual links here. And so here it's pretty easy to spot all of the related items, right? But there's one problem. If we look closely, we can see that these links introduce quite a bit of clutter. So they're not like, in this case, they occlude the text here. And that is of course not great. You want something that is great at highlighting, but still subtle and doesn't include any other information. And so what we did is we created an algorithm that routed them into these links into regions that were like where there was no or very little disturbance. So here, that's kind of an optimization problem. We measured the contrast between the background and other like features that stand out, and then ran an optimization algorithm to find the optimal route that minimally occludes the information. So that's what we studied, and we found that with eye tracking experiments, we found that this works, for example, equally well compared to the straight lines, but of course significantly less occludes the information. So the takeaways from this perception lecture is that knowing about perception is really important for visualization, but it's also important for user interface design in general. How do you choose your colors? How do you show relationships? How do you draw attention to something that you want your user to pay attention to? And how do you minimize the risk of your user overlooking something that you consider to be important? Good. So that was the perception lecture. Now we have time to go into the data lecture. And I'll start the data lecture with a design critique. Oh, by the way, the How to Slice Obama's Budget came back. Forwards. So here it is in all its glory. So it is interactive. You can hover over these dots, and then when you switch between them, they have these nice transitions. So I can switch between all spending, then between types of spending. And so here we have, like, I didn't show that on the paper print. Here we have mandatory spending, and here we have discretionary spending. Then it transitions to changes. And you see that the discretionary, the mandatory spending is removed here. And then we have the departmental totals. So you basically saw it, but it's of course much nicer if it's interactive. And I feel like I'm personally responsible for this breaking because I tweeted at the New York Times graphics department in the morning that their other graphic isn't working. And half an hour after I tweeted that, many of the other graphics were not working. So I think they tried to fix something and broke more stuff. Well, the cars is still not working. Okay, today's design critique is a little bit different and it doesn't rely on an external website. Currently there's some missing over here. So, before you read this in detail, I'll play you a video, because this is an interactive animated technique, or it's an animated technique, not an interactive technique.
Hi, I'm Michael Ogawa, creator of CodeSwarm. This video is meant to be a companion to our paper, so it assumes some basic knowledge about our visualization technique. Due to the size limitation on videos, we cannot cover everything we wanted to. For the full story, please visit the CodeSwarm website to see the original videos. The story of Python begins with Guido van Rossum, working alone in the late 1980s. He is Python's creator and benevolent dictator for life. A year later, 2 developers join him, but they stay on the periphery of the swarm. One of them, Jack Jansen, created MacPython. His activity stands out because his sphere of influence periodically converges and diverges with Guido's. Another person, Fred Drake, appears and commits mostly blue document files. Indeed, he will become the lead documenter of Python. This pattern of Guido being the clear central developer with specialists on the periphery continues. In the year 2000, the popularity of Python takes off. We see many new developers coming in as the project activity increases dramatically. And for the rest of the video, the project stays busy. The Eclipse project is vastly different than Python. Right away, there is a flurry of activity. Many developers working on many files at nearly a constant pace. This is possible because these people were already working on the same project before Eclipse was open sourced. We also see that, even amid the chaos, the Eclipse project is made of many components, There are many developers clustering around the center, yet they each have their own set of files. In other words, there is not one large set of files being worked on by everybody, but many small sets of files being worked on by individuals. This can be attributed to Eclipse's rich client platform, which facilitates modular design. Looking at the commit histogram, we see something not apparent in the Python video: weekends and holidays. Weekends are the periodic gaps in the histogram occurring every 7 days. The holidays can be seen at the end of December throughout the video. These breaks further reinforce the idea that Eclipse is developed with corporate sponsorship. This final video was not produced by us, but was made after we open-sourced CodeSwarm. Alex Evans, co-founder of MediaMolek.
So I'm gonna, there's nothing new in here. Take a couple of minutes, look at one of the, or two of the other videos, and I didn't explain what the visualization is about yet. Try to guess and understand what the visualization is about, how the various attributes are used, and so on, and then we'll discuss it in 5 minutes. You're encouraged to do this in teams. Okay, so what is the data that we see in this visualization? Well, and by the way, something like this is like 100% going to be on the exam, or on both midterms. Like both midterms, there will be design studies. I'll give you a visualization, and then you will be asked to critique them and make suggestions to improve them. And so what you should do there is you should, like by now we're doing this informally, but then we like you already know about perceptual aspects, and then next week we'll learn about efficient visual encodings and so on. And so you should always make these arguments with respect to the theory that we learned. Why is it bad? Why is it good? And so on. So if you kind of like replicate one of the discussions that we have here in the classroom for your midterm, then you will be doing great on this question. Okay, so what is the data that's encoded here? What's that?
The color of the dog.
But it's not the, I mean the data, what is the source?
Oh.
The amount of work, but how do you, like, what is the, like, it's hard to measure, right, the amount of work. How is it measured?
The commits of the GitHub.
Yeah, it's commits to a software project. I don't think it's GitHub because it's old. This is 1998, so it's probably a version control like SVN or CVS. Do you have another comment?
I was just going to say commits.
Yeah, commits over time. And so what are the attributes that we see here?
Colors of file types.
Exactly, so we have file types, and the file types are encoded as color. What else?
The developers.
Exactly, we have the developers as like labels. Anything else?
Time of the commit.
Yeah, so we see the time of the commit by, like, in the one hand, by the animation when they appear, so it's kind of like an accelerated timeline, and they appear at the time relative to the video speed. But we also have like a linear representation of the time here on the histogram. Anything else that is interesting? What else is encoded in this histogram?
The time and the maximum number of comments were made.
Yeah, I'm not 100% sure whether it's the number of commits. My guess would be is this the size of the commit, like how much text was changed in a specific commit. But yeah, that's closely related.
Also shows like who was working together on what.
Yes. So it shows ownership of the files, who worked on what, and so how is that shown?
Just by the position.
Yeah, position. And so position is used here to show the relationship of who is the owner or who is the author of a file and the file. But it is not like just like attracting force, right? It's not something like absolute, but it's kind of like this fuzzy force. So what do you think about this? Like, do you think you can read data precisely here? No. So what's the purpose of this visualization? Grab attention there, yeah?
Find out the different amount of words at different period of time.
Yep.
The timeline of the progress.
Yep.
I wonder if this is only meant to be used while someone's like telling the story. It's like something for us to look at while they're describing it.
That is a good argument. So you're mainly saying this is more for communication and not for real exploration?
Yeah.
I was just going to say, there's something like this that shows the exact files that are made and like where they are in relation to the project. So that might be something that would be a better way to see what's exactly going on without reading.
So you mean something that shows you more about the structure of the project itself? So what is interesting here is that this doesn't actually show you the files in the project, because if you notice, they fade out the points. So if you don't work on a file, they disappear and they only reappear when they fade in. So I don't think it was the intention of the developer here to show us the structure of the project. Yep.
I think it's more like a general overview of how the project is constructed in relation to the developers.
Yes.
Seems also like comparing different softwares and how they are constructed.
Yeah. Yeah, so this kind of like brings me to the next point. This visualization was really popular when it appeared and was widely used by many people in the open source community. Why do you think that is? Did you think that people really like learned something about their project and said, okay, we need to do this differently?
Looks cool.
Yeah, so that could be the answer, right?
So from my point of view as a Python user, I look at it and say, okay, Python is this big project, whoever wants to do it can just jump in and do it, whereas Eclipse, since it was that constant body of core people, is like, okay, I'm not one of them, so I never have a chance of working on Eclipse unless I get the one specific job.
Yeah.
But I can do Python stuff, whoever I can.
That's true, yeah.
I think maybe it gives people a sense too of the fact that they're not working in isolation a little more so. You kind of see this huge body of work and like you feel like you're a part of something.
Yeah, community building. So it's more of like a soft goal visualization. It's not something like that you would say, okay, we have not done the software engineering process accurately. But you can see some aspects of how things are engineered, right? But it's not something that I think is super actionable. So this was kind of like a movement a couple of years ago that was called like organic visualization, where this wasn't about creating like hard fact visualization, but kind of like bridge a bit the space between art and data visualization. So anybody want to share their personal opinion? Is this a good visualization or a bad visualization?
I think screenshots are bad. I get no information about it, but once the video is playing, it's pretty useful. I think it comes across well.
Okay. Any other opinions? Anybody want to speak up against it?
Would it be better if it was like an interactive thing with a slider on?
Probably, yeah.
I feel like there's, even with the video playing and the audio, it's still a lot of information trying to parse without a lot of intuitive ability to decipher what's going on. Other than like, okay, yeah, I can see a lot of stuff's happening versus 15 minutes ago.
Yep.
Yeah, I kind of build on top of his. If you don't understand coding, you have no idea what's going on.
But are you the audience then? Do you care about this?
Well, I feel like good visualizations don't have, would try to encapsulate as broad an audience as possible.
Well, I tend to agree. It should make it accessible to as broad an audience as possible. But if you don't know what the data is, right, it doesn't make much sense.
I think my biggest issue with it is that it's not curated. If you're trying to tell a narrative, if you're trying to tell a story and show something, there's just an overload of information, and there's a lot of motion, and all of it's very kind of fine, fuzzy details that you can't fixate on, you can't really show much with it.
So what you're saying is that you cannot ask specific questions?
You can't ask, well, not that you can't ask specific questions, but that there's an overabundance of information that's seems meaningless to your story. You know.
I'd argue that that's not a bad thing, because that provides context and setting to a certain extent. Maybe you're not supposed to get all of that information out of it, but it helps you get kind of a general idea of what's going on. Like, you go to Disneyland, Pirates of the Caribbean, you're not going to notice half the stuff that's in there, but it makes it look like a pirate town, so the rest of it's believable.
Okay.
I find it's not initially intuitive. So I sat and watched it, and then it gave the explanations at each point, and then I went back again and watched it. And then it becomes very, very powerful. So initially, I have no idea what it is, honestly.
Yeah.
It takes an entire explanation to do it, but then I went back at it, and then then the features start to pop out once they've been explained to you. And then afterwards, I like it. So I guess my only critique is that it's not initially intuitive. It takes a few run-throughs to figure out what it's showing. But once you figure that out, I think it is effective at communicating what it's trying to communicate.
Okay, great.
The thing that I didn't like about this visualization was that there was too much planes and too much clarity going on the visualization. And I'm not sure if it is okay or not, but I don't like it.
Too much what? What was it?
Blurry things.
Blurry things. Okay. Yeah. Yeah. So I guess this is the kind of like the piece that we'll be discussing that is the most artsy. And as you can see, art is subjective. And so we have this interesting range of opinions of who what people think about it. And I think it's just like really at this space where it's not about hard facts, it's more about giving you like a feeling of what the project, what software development is like. So I think that Hollywood would be happy with doing such a visualization in one of their movies to show the software development process, right?
I had a question. Why is there so much focus on the center? Like, why are the developers fighting to get to the center?
This is probably just an implementation detail. So how the forces are, like, if you remember Carolina's explanation of how you center a graph, that you have some force in the middle, and so I would assume that all of these developers push towards the center unless they work on unless the forces that they work on different files kind of repel each other much more. So those two guys here seem to partially work on the same files, but yeah, I don't have insights in the exact algorithm. Okay, so yeah, this is something completely different. Any last words on this?
There was a Linux kernel similar to this that was like over an hour long.
Yeah, you can now generate those videos. I don't know whether it still works, but you can generate those videos so you can make them long and you can watch. I don't know whether you want to hold attention for an hour. But
I think one important thing in video visualization is what you can remember after that, because you don't want to play it all over again. So for this case, I think there is very few things that you can remember after watching it once, and it's like for 5 minutes.
yeah, well, you could say that the goal wasn't to show you that this person edited the file, but was more to show you how the structure of the project was, right? And I think that you probably know what is the difference between Python and Eclipse in terms of development model. Do you know that? Do you remember that? No? Okay, well, answering this kind of question, that's an important question for any visualization. Like, how do we retain information? How do we how memorable is it, and so on. There's many factors. Like, I'm mainly actually in this lecture talking about possibly precision of understanding the information, but I'm not necessarily talking too much about retention, like long-term recall. Long-term recall is just a really fuzzy thing, where it strongly depends on how important the data is to you, for example. Like, how important is this fact? So it's more of this data-driven thing, less the visualization. But we'll have examples in 2 lectures where we talk about what can we do to make charts memorable. Yeah?
Now that you bring it up, I feel like the thing that I really struggled with is I didn't understand, like, when you're generating a report, whether it's like text or visual like this, you need to have some type of thesis, right? I feel like you really didn't give a good idea of what I wanted you to learn.
Yeah.
And if this says, okay, this is what I want you to learn, and then kind of can wrap it up at the end, it's
Yeah.
in a visual manner.
So
It's
maybe-
a lot easier to extract the data.
Maybe in this case it was my fault. I should have probably given you like 2 sentences about what this visualization does and is supposed to do before actually plunging you into this. And my assumption is that most charts or videos would have a title, and the video didn't do a good job at explaining what its goals and motives and the source of the data was and so on. Okay, so let's move on to some more fundamental things. We'll talk the rest of this lecture, and we'll talk about data. So a couple of terms, and now this is really well written down in the visualization book by Tamara Mansner. So the dataset types and the data type are something that we really want to distinguish here. The dataset types describe what can be visualized, and the data types describe fundamental units and the combinations that make up the dataset types. And so the dataset types that you can classify is tables, networks, and their variety trees. For tables, there would be the variety multidimensional table. Then fields, where you have grids of positions and then points on each of these fields. And then geometries, like the shape of how things are positioned relative to each other. And in terms of data types, this is different from data types in programming languages. We have items, attributes, links, positions, and grids. So these are the fundamental data types that we observe, and we can represent them in very different ways. So there is a difference between structured data and unstructured data, and so here I was mainly talking about structured data. Structured data are exactly these things where we have like a clear way of like structuring things. Of course, we have tables where we have rows and columns, we have networks where we have relationships, fields and grids, and so on. All of these is very structured. Most data that we actually record on our computers is actually unstructured. So we don't have a predefined data model. We simply collect it. So that could be, for example, text. Text is text heavy, and then we have some facts in there, dates, times, and locations, and so on. Another data source that is largely unstructured is videos and images. So these things are hard to extract information out of them. And so this translation from unstructured data into structured data are actually major research fields in computer science. So for example, getting structure out of text is what natural language processing cares about, or text mining, or sentiment analysis, or getting structure out of video or images is what computer vision or image analysis cares about. So what we will do in this class, we will mainly look at structured data and will only not really touch into how to transform unstructured data into structured data. But once you have derived the structure from the data, you can actually visualize it. So here's an example. This is a graph of who beget whom, so whose father or child in the Bible. So the source here is King James Bible, and the pattern that was searched for is X beget Y. And so you can see that we have like a very long family here from Elazar to Oili to Archim and so on. And then we have the visual encoding, like Abraham, for example. It's the size of the label is scaled by how often this person is mentioned. And so we see this Abraham, Isaac, Jacob relationship, and then we see that this Azariah here is has many family ties, many family relationships. And so here, what Oda did is create a very, very simple rule, X beget Y, and then threw a big text corpora at it. And by that, we essentially can extract a graph. So we can we get structured data out of that, and we can then visualize the structured data. Here's another example. X is Y. This is our 18th and 19th century novel. And so an interesting artifact that I like to point out here is how bride and wife are differently associated. So the wife is usually associated with respectful people like the banker, the merchant, the ambassador, the father. The bride instead is the pirate's bride, the freebooter's bride, the bandit's bride, or the sailor's bride. So these kinds of relationships is what you can get out of this. And again, no fancy machine learning or NLP methods, it's just like very simple rule parsing. Data have semantics, and the semantics are something that computers usually are not great at capturing. So if I have this data vector here, Basil 7S peer, what does it mean? It's kind of meaningless for us. It could be like the name, a city, a fruit, height, age, day of month. So what we need here is metadata that describes what this means. And so here, like if we have a table like this, we have the header, and the header describes this metadata. So the first column here, after the ID is the name, then the age, then the shirt size, and then the favorite fruit. And now we understand what this data means. So like having these semantics is actually not important for you to plot the data, but it's important for anybody to understand anything about your data. And if you don't give people, for example, legend or scales, or axes, then they will not get the semantics of the data. So you would always need to label everything. So the data types are really structural or mathematical interpretation of data. There are things like items, links, attributes, positions, and grids. And this is really important to understand that this is not related to the data types in programming. So for example, a link can be an integer. It can be a string. So the link could be a pointer. For many cases, we have many different data types, computer data types, or programming language data types to distinguish them from these conceptual data types. And so there's a difference between items and attributes, and I also like to think of these as independent and dependent variables. So the item is an individual discrete entity. For example, a patient, a car, the stock, a city. And the attribute is something that is measured for this particular item or for this independent variable. And it's something logged. So for example, for the patient, that would be the height or the blood pressure. For a car, that would be the horsepower or the make. And of course, what I consider as my independent variable can vary. For example, I can tag time as a dependent variable, but if I collect my data, like for example, I want to test blood pressure over time, then I would have the items would be these time points. So this is a flexible definition. So here we would have the item be a person, and these would be the attributes here. And then this would be the cell theorem. This is kind of obvious, but I just wanted to be explicit about the terminology. Other data types are links, which are really about expressing relationships between two items. So we'll see that a lot in graphs, of course. The friendships on Facebook, your relationship to the university, your relationship to your colleagues, your partner in your group for your final project. These are all links that you can model as links. And so these kind of relationship data is becoming more important, and we're collecting more of these relationship data because we're collecting so much information about our world. Positions are really spatial data. We have a location in 2D or in 3D, so we will be mainly working with maps in the first 3/4 of this lecture, but then we will also do 3D volumes and flow in 3D and so on. So this could be things like pixels in a photo, voxels, these volume pixels in an MRI scan, or the latitude or longitude in a map. And the grids are more like describe more of a sampling strategy for continuous data. So for example, what grid am I using in my MRI machine? How fine grained can I collect that? Or the positions of weather stations in the United States. Okay, let's talk a bit more about these major dataset types. So tables, there's like the flat table where we have one item per row, and each column is an attribute. And tables have a unique or key, but importantly, this can also be an implicit key. So it could be the position of this item in the row. That's what an implicit key is called. And typically, those tables shouldn't have duplicates. In multidimensional tables, we have indexing based on multiple keys. So I'll show you examples for those. But first, like here we have the item. Here we have the values. And then here, this is the key. Here, this is a unique key in the table. And together, those are the attributes. This is a multidimensional table. So here we don't have one item and then a number of observations, but we actually have two different keys. So we have keys patients, and then we have keys genes, and these are gene expression values for all of these patients. And so what we can do in this table is we only have now one data type, right? So we have, like, for example, this is always the combination of a gene to a person. And in these other tables, we can have more complex data types, right? We have strings here, we have numbers here, and so on. In a multidimensional table, I can only represent one data type per table. And what I do, if I need multiple dimensions, then I stack those tables. I create multiple of them and then show like them essentially, like how I show them is a different question. But here are a couple of examples of how we can visualize table. So this here is a parallel coordinates view, and we'll talk more about this in the lecture on tables and high-dimensional data. But just to give you an intuition, so in this parallel coordinates plot, this is D3. What is done here is that each dimension, each attribute has its own axis, but the axis doesn't have to be of the same data type. So we have here miles per gallon, cylinders, displacement, the horsepower, the weight, the acceleration, and the build of the car. And so we can trace, by looking at these polylines, we can trace a car with a high miles per gallon range usually has not 8 cylinders. So there's no high miles per gallon car with 8 cylinders. And then we can continue looking at what is the trends that we see here. So we see that there is like an inversion between weight and acceleration. It's like an inverse relationship. And so in this chart, we should also be able to brush these elements. And so we see now cars with high miles per gallon have few cylinders, don't have a lot of displacement, don't have a lot of power, don't have a lot of weight, and are not the fastest to accelerate. None of this is surprising, but you should be like, this is easy to see with this visualization technique. And if I go in the other way and look at the gas guzzlers, we see that they usually have 8 cylinders. And that they have a lot of displacement and a lot of horsepower and so on. Here's a more explicit representation of a table where just simply we have years and then we have these bubbles, and the bubbles correspond to something, and then on hover we see we can actually switch to the numbers. So this is like just another example, and we'll talk more about more advanced ways and details about all of these visualization techniques in the table lecture. Graphs and networks are a very important data structure, as I already mentioned. Formally, a graph consists of a set of vertices and a set of edges. So usually when you have, if you look at the data structure, how a graph is stored in a file, you first have a list of nodes, maybe with attributes, and then you have a list of links, and then the links are usually like node 1 to node 2. So this is how these graphs are stored typically. A couple of definitions on a graph. So a simple graph is a graph which contains no multi-edges and no loops. So many graphs that we will be working with are simple graphs. And there's a lot of special graphs, and the most important one here is a tree. Like a tree is a kind of graph with no cycles. And this property of it not having cycles makes it amenable to very specialized visualization techniques that are really optimized for visualizing trees. And then we have directed graphs, where we distinguish between a connection from A to B and from B to A. So in this case, if I have an edge that connects A to B, it doesn't mean in a directed graph that we also have a connection from B to A. So we need to make explicit edges about this. And then hypergraphs are graphs with edges that connect any number of vertices. So let's say I have 3 students and you are all in this classroom, then that would be a hypergraph that connects you. You can think of a hypergraph as like a hyper edge, or you can also think of it as a set relationship. I usually tend to prefer to think of it as set relationships between the items rather than hypergraphs, but you can formulate this in terms of graphs. Another special thing is a bipartite graph where vertices connect, vertices can be partitioned into 2 sets, and there is only connections between those 2 sets but not within these sets. And this is surprisingly common, and it's an interesting research area too. And like just a couple of terms on graph properties. Like an articulation point is a vertex which is deleted from the graph, would break up a connected graph into multiple graphs or an unconnected graph. So here would be the articulation point in this figure. If we remove this, we had this connected graph broken up into 2 pieces, like piece 1 and piece 2. There is many different ways to visualize graphs, and we'll have 2 lectures on this. One of them, and we've already seen this, is the node link diagram. So this is the standard example that everybody thinks of if we think about graph visualization, but there's also others. This one, matrices, co-occurrence matrices, this actually shows you the same data as the previous graph. And these matrices, they essentially fill in a cell if there is an edge between actor A and actor B in this case, or character A and character B. These are great for seeing certain kinds of structures, but they're extremely dependent on the ordering. So for example, if I order this by name here, we don't see much structure. But if we order this by clusters, we see quite a lot of structure. So we suddenly see like these groups of people that co-occur a lot. And so here is the main actor of Les Miserables, Jean Valjean, and not surprisingly, he interacts with quite many people. So these matrices are great for like seeing these one-hop relationships, but they're terrible at showing topology. So like a distance of 2 or 3 is almost impossible to trace unless you really sit down with a pen. A special case for trees are tree maps. And so tree maps represent like a hierarchy by using the squares and then visualize the attributes of this hierarchy. So here is who imported coffee that was not roasted in 2012, and you see that Germany imports a lot of coffee, and United States import a lot of coffee, but other countries like the United Kingdom, where you would expect they're roughly the same size as Germany, but they seem to prefer the tea over coffee. And so you see the hierarchy here, the tree here is the continents, and the size here are the attributes of the tree. So this is just one of the tree visualization techniques. And the homework 4 will actually have a very simple tree, but it's just going to be like a tree that you, as you would expect it, like a node-linked tree. More about all of this in the lecture on graphs and trees. So fields in fields, what we really care about is to sample from a continuous domain. So here, for example, we have a map of weather stations across the United States, and what we are interested in are parameters like temperature, pressure, wind velocity, and so on. And fields can be measured or simulated, but the big problem when we deal with fields is that we often have a sampling problem. So in Nevada here, for example, you see that there's not a lot of these weather stations. So what is the temperature here at this point? Like, it's a question that is hard to answer. We have to think about interpolation strategies for that. How can we answer that? And so this is more like the area of signal processing and statistics. We'll not be doing much of this sampling and interpolation. There will be some of it in the last part of the lecture. Fields often come, or always come in one of these grid types, but they're very different from like how easy they are to work with and what they can do. It's like a uniform grid is where we simply like have something like this, a very clear uniform grid where we can compute both the geometry and the topology. So we have a very regular sampling. We can have a rectilinear grid where we can do non-uniform sampling. So if we, for example, know in our CT scan, I'm going to get like an overview of the whole, like say head, but then I really want to focus on one region of the brain, and I'm going to do more focused, more fine-grained scan there. Then you could have something like this kind of rectilinear grid. You could have a structured grid. Here, as you can see, this curvilinear grid. So we have some kind of structure, but it's not like rectangular. It's kind of rare. The major other class are unstructured grid. And unstructured grids are super flexible and are very popular, but they're also computationally the most expensive. I have to explicitly store the position and the connection, so it's more like a graph. I cannot, like, just by knowing that I have this node, there's no easy way of telling me its relationships unless I store them. Here are 2 examples of visualizing fields. This is an MRI scan of a head and the chest, and by simply, like, this is one data set, all of these 5 pictures, and by simply modulating a transfer function, we can get these different images. So we are emphasizing different density values by saying which of these density values do we want to map to a specific color, to a specific alpha value. And so here we have a wind map, and as you probably clearly understand, we don't have we don't have detailed information at any of those points, right? So we kind of interpolate and sample here. Let me see, this wind map is also live. So this is a live wind map, and this is what's called flow visualization. You can see that there's not a lot of wind right now. Oh, we're around roughly here, so there's a bit of wind. There's a legend, and there's a couple of big, this is Hurricane Sandy historic data. So I can see that very well. Geometry are not a core visualization topic. It's about the shape of items. It is kind of somewhat important in like visualizing. For example, you can always say, I want to create a geometry that describes the hull of this person's head. But typically, this is more the area of computer graphics and CAD. So we have like the Stanford Bunny here. We have like an engine in CAD. Where we will kind of, where you're already working with geometry is of course maps. So we have these explicit spatial positions and their relationships, but we other than using them and referencing on them, we'll be not doing much to it. I kind of wanted to give like a side note on academic trenches. These different fields, they have different communities. Information visualization is about representing abstract data like tables and graphs. And so that's what the first part of this lecture is mainly on, or let's say what we'll start talking about in 2 weeks. And what makes these interesting is the freedom to choose the spatial layout, that this was distinguishes them. Like if I have a scan of a brain and I choose where to place my pixels, it's not going to be super helpful. But if I have a table of heights of people, then I can choose how to plot them. So there's more creativity and less mathematical, just describing the reality. And so humans play a bigger role, understanding how humans perceive things and so on. The second academic trench is visual analytics. This is kind of a combination of information visualization with machine learning and is more amenable for applied work. And my not so nice criticism of this field would be that it's more like a funding buzzword rather than really an academic field by itself. And then finally there's scientific visualization, historic name. And this is really about spatial data, like fields. And here you're not free to choose your spatial layer, and it's about finding the best way to depict reality. If I were to look at a set of images and decide whether they're scientific visualization or information visualization, I could build like probably the most trivial classifier ever. I could simply look at what is the dominant color. If the dominant color is black, it's going to be scientific visualization because these people like black backgrounds. And if it's white, it's information visualization. And so here's a random Google search of information visualization and scientific visualization to show you that this classifier would actually work pretty well. There's of course exceptions. Here we have a black background and here we have a white background. But generally, if you see black background and many colors, it is scientific visualization. If it's white, then it's information visualization. Other collection types that are super important are sets and lists. You have an implicit understanding of them from programming. We will talk about visualization techniques for those. And then, of course, clusters are very important. Groups of similar items, any kind of grouping structures. And clusters and sets are, of course, closely related. However, clusters are usually not explicitly defined. So let's look at the time. We have a couple of minutes left. I have 50 slides. Well, we can talk briefly about attribute types. So in terms of attribute types, there is like two main distinctions. There is categorical and quantitative. And ordered ordinal can be sometimes classified as part of categorical. So what do you mean by these? Categorical would be something like fruit, gender, movie, genres, file types. So there is no bigger than relationship between them. These are just distinct classes. There is no order. There is no like fruit plus gender doesn't make sense. This is just like there's nothing there where we can make any relationship assumptions. With ordinal data, we don't have an explicit definition of what is bigger or smaller, but we do have an explicit definition of what is bigger or smaller, but we cannot do math on it. So we have things like shirt sizes, for example, or rankings. Like the university ranked at number 1 is not 15 times or n times better than the university ranked at number 2. And then finally we have quantitative data where we can do any kind of arithmetic, where we have like things, for example, like length, weight, and count. So these are kind of the attribute types that we're most familiar with, I guess. For quantitative data, there is a further distinction between interval and ratio data, and that is kind of something that is not immediately intuitive. The main question that you can ask yourself if you look at data and want to understand whether it's interval data is, does 0 mean none? Like if we have 0 degrees Fahrenheit, we don't have no temperature. It's just like it's some preconceived convention. And Fahrenheit, for example, is a good example because we have actually for centigrade, we have like different 0 points. So 0 in centigrade is defined as freezing of water, and 100 is defined as boiling of water. I don't know what 0 in Fahrenheit, like the stories that I hear is that the guy Fahrenheit who invented the scale simply looked at the thermometer and said, okay, it's not going to get colder than today, and that's where we have 0. So this is a very arbitrary definition. 100 degrees corresponds to body temperature, but 0 here is meaningless. And so when 0 doesn't have a meaning, then it's an interval scale. And we cannot compare them directly, so we can compare only differences in intervals. Ratios have a meaningful 0. So there is something like length 0, length weight 0. There's simply nothing there. If nothing is nothing, or 0 is nothing, then it's usually a ratio scale. And there we can do math on it. We can do, like here we can do relative comparison, but we cannot do general division, for example. But here we can do any kind of mathematical operations. And so we'll talk more about this on Thursday. I'll catch up with the rest of this lecture and then talk about visual encodings.